Good morning everyone, my name is Anjulesh Kushwaha. Today I am excited to walk through my engineering life cycle of my internship project, real-time EV ADAS dashboard system. In modern electric vehicle safety system, powertrain electronic cannot operate slowly and they require tight microsecond level synchronization. Over the next few minutes, I will show how I design a bar metal frame where architecture that handle the real-time vehicle physical model integrated active multi-sensor separate scanning era for the collision avoidance and history defense telemetry data with the zero processor latency. Let's initialize the system architecture and to take a look at the fundamentals of project. System architecture. In the system architecture, automatic embedded system internship journey. To kick off my intensive journey, this slide highlights the core foundation and integration of the project conducted the emerging information technology. That technology developed was built on the ARM Cortex M3 architecture using an STM32 Blue Pill microcontroller because we were working in the simulated automotive workflow. I leveraged the Pixel Lab ecosystem to validate the pin-out and simple continuous analog signal voltage and the test software execution time. The core breakthrough of project was integration treat the powertrain and safety feature and separate entity. The firmware blind the vehicle dynamically physical directive with a separate ADAS scanning era creating a highly integrated real-time safety network that's mirror modern EV control architecture. Intensive roadmap and development. And move into the specific timeline of my timeline. Move into the specific timeline of my engineering cycle of divided into core phase. Phase 1 focus entire setting up to the bar metal architecture that establishes our primary real time schedule tracking using hardware timer time 1 and time 4 to increase strict execution loop time and host 3 shift to focus the power and mono. Here I am configure the multiple channel 12 bits ADAS group of sample real time virtual loop break potentiometer data feeding through raw input into our localized vehicle physical logic. And phase 4 5 6 into the active safety layer. I built drove 3 distinct ultrasonic sensors to run simultaneously, scanning around the parameters and vehicle manage the distance logic along with the fault manage rule. Phase 7 and 9 focus on the engineering serialized pipeline by the shifting away from the standard block print loop and minor non-blocking DMA channel that microcontroller was unable to stream high density data directly into the custom Python visual interface at steady 100 megahertz. Now move next slide. Core embed technical competency. This slide outlines the core embed competency I mastered by the engineering. The system architecture embed C hall. I initialize the system hall driven handle low level resistance architecture. This keep the code base clear allow me focus on the creating efficiency high level frame where logic interrupts ISR to ensure the true real time system configure hardware time interrupts to unfocused strict schedule the vehicle mathematical physical model running on the precise 10 milliseconds loop time via time 1 vehicle, and the ultrasonic sensor pulled on the 100 millisecond loop via time 3 to capture the deterministic separate feedback. DMA transmission. Instead of using block print function that waste value CPU cycle, I implement a direct memory access. The CPU simply format the telemetry package and handle them over the DMA hardware, which stream the raw bytes over UART in the background with zero processor latency. Modern architecture. To follow projection architecture standard, the firmware enters display into a organization multi-file project structure by the cleaning separate model like EB control.c and ADAS.c, ensuring high code reliable, easy and debugging, distinct decoupling across the different automatic domain. Physical based EV control subsystem. Now let's dive into the subsystem. First, the physical based EV control subsystem, rather than using the arbitrary on the linear scaling factor of the simulated speed and the battery consumption, I program the actual automatic equation into the firmware. First, I implement the lamped inertial speed model. Using the neural integration, the ECU calculate the true linear velocity every 10 milliseconds by the balancing the commands motor torque and against the aerodynamic track and ruling the resistance variables. Second, energy module computing the real-time battery state of charge of his SoC by the tracking mechanical work combined with I square R motor copper loss model. Batteries simulate true physical behavior for the instant of if you stand on the battleground and while holding the vehicle at the instant with the brake and the brake train resisting due to the active electrical thermal loss. Finally, we have active regeneration braking engine, where I pedal difference across the 5% threshold and motor applied negative torque up to the 18 Newton per meter. This serves as the current flow recapture kinetic energy charge simulate battery package of the fly at threshold behavioral shift across three distinct efficiency driver mode. ECU while limits torque to 0.6 multiplier of the range and the normal for the standard mapping and sport which unless 1.3 performance boost. Ultrasonic ADAS radar engine. Moving to subsystem 2. We have ultrasonic sensor radar engine that model handle precise the spatial awareness using the three sensor configured to the track obstacle around the front, left and right segment of the vehicle. The common pitfall in the basic warning system relies strictly on the fixed destination value instead of a design time of collision predictive engine, and you should calculate relative collision speed and assign how quickly target distance is changing over the time. This means if the obstacle approaching rapidly, the safety threshold scale toward the issue early and the visual alert before the collision become late. Additionally, I implement a smart logic filter specifies road scanning that blind spot system monitoring side zone but stay moderate during the peak management implies false alarm. Its alarm automatically once vehicle velocity across 20 km hertz consistently when going under the 10 km. Then the system active parking assign mode and the converting our eco metal into the user friendly 0.1 or index for the precising parking. Fault management and safety rule engine. This brings to the core defensive software layer of the project. The fault management and safety rule engine in the automatic software engineering code must remain complete and predictable under the worst cases failure. Fault diagnostic. To the manage the multiple error at once without having bit filled fault resistance. This signal vary according to the track concept validates specific bit miles 0.0x01 for the motor over temperature and 0x02 for critical SOC and for implementing front collision 0.04. Safe statement environment. If the fault is officially valid, then a central statement drop out the driven loop and architecture for safety roundup, configure immediate motor cutoff, dropping PWM signal 0.0% within the string 10 millisecond cycle, physical component, ensuring total vehicle safety. Host target telemetry and pipeline. Now let's examine the host target and telemetry pipeline, which serve as a data highway between the STM32 microcontroller and external host PC. Physical layout. For our hardware link configure UART 1 to operate at 11,52,000 bits per second using instead of 8 and 1 frame layout. This ensures highly reliable and serial connection across the physical COM port without risking byte swap. Serialization to the maximum bus efficiency, data avoidance transmission raw SI to the text string, which creates a major component overhead. Instead of the frame implement data and specialize it to type packet of the core parameter into the light bring frame transmission 0x01 pack for the continuous GB matter and 0.0x04 pack ADAS alert at 10 Hz, and this is the supplementary by the synchronized 0x04 the state pack that frame state of charge change to the given HMI immediate update testing say to ensure the safety engine diagnostic the communication loop is just one way development interrupts driven X ring buffer system on the target side. This run at active terminal cell allows the develop inject testing string like over live sensor distance maker and instead of evaluate how the vehicle math handle has case for trigger. UI visualization and testing dashboard. Now let's review the final interface layer of UI visualization and testing dashboard to complete our high performance embed target. I developed dashboard telemetry cockpit using the Python and Matplotlib. This HMI read incoming non-blocking binary data stream from the serial port, pairs this dynamically and refers the graphical dynamic speedometer. color code safety across green and amber red for the velocity thrust. And Tesla style battery origin. This component acts as our core energy displays procedure and increase package symmetry to the track state of charging and highlight the active driven profile with ECU normal of sport scale the remain range step dynamically. Bird's eye view. Finally, in the bottom right sector of the interface, handle the separate radar reading the at the instead of the millisecond echolocation delay for our front and left right ultrasonic sensor ray into the instrument real-time top-down map with view automatic flash warning when if a vehicle crept into our blind stop on highway. Now we move towards the project demo. And this is the STM3532 microcontroller, and this is the spare part of our actual circuit, and this is the virtual terminal where show our microcontroller all data here. This is the left side distance detecting ultrasonic sensor has increased distance and decrease by this slider, and here automatic data will be shown. And this is the front side ultrasonic sensor, right side ultrasonic sensor. This is the acceleration pedal. Acceleration you can increase and decrease. This is the brake pedal. This is SOC, state of charge. This is the motor temperature, can be increased and decreased. And this is the when the front side any obstacle come towards the our EV, then this red LED show our collision, and this LED show critical condition. And when right side any obstacle comes towards our EV, then green LED will indicate blind spot detected on right side. And this is the left side sensor. When obstacle comes towards the EV, then blue LED will be on. Okay, it will be automatic off. This is the virtual terminal where show the torque, motor temperature, range and driving with normal, sport, acceleration pattern 99% and brake 0%. As increase brake pedal, then brake will be also increased. And brake pedal. And this is the front and left right side distance. So as a front side 321, and this is the collision and TT, any time to collision 0.0 second, alarm advisory, and the fault flag 0.1. So active 1 and increase This will be so hot. Now we move towards the our actual dashboard. This is the view of our dashboard, where this is the speedometer, show the actual speed of our EV, and this is the so percentage of battery SOC. And this is the mode. This is a range so that covered by the EV at this charging level. This is the speed history that show the speed of the previous time, and this is the EV matrix where so torque, as torque increases, speed is increasing, then torque will also increase. This is the critical conditions of torque is 0. This is the normal conditions, and you can see torque here -6 due to the brake pedal, and brake pedal 0%, then torque is 131, and this is the brake 0%, and motor temperature 25, and motor temperature increase. And here so critical condition and motor temperature also increase here simultaneously, and alarm show advisory, and false also 0.01 when motor temperature decrease, then alarm will be 000, and this is the signal. This is our actual EV, and this is the front obstacle has decreased front obstacle. This will become towards our EV. You can see here when decrease left side, then obstacle come towards the left side, and when we come the range of ultrasonic sensor right side, then right side's obstacle come here, and also alarm so critical because obstacle left side and right side come towards our EV, and here so also yellow light on, and our whole dashboard will blink when the front collision will occur. You can see our whole dashboard will be blinking on 15 centimeter, and time to collision so here 0.0 second, and the speed of the vehicle here. When negative torque is applied, the battery will be automatically charged here, so negative torque when temperature and everything is okay. For here left hand, you can see here automatically battery will charge. Everything normal condition, alarm is advisory, and battery here charge. Engine condition, you can see battery level is increases because of negative torque. Acceleration will be increased, then level also will be decreases at so fast because of speed is very high and acceleration pedal 100% and brake pedal 0 and maximum torque of 150. Now we watch the next slide. Key and challenges and solution. Now that we see the live environment of the action, I want to wrap by talking about the core engineering challenges I faced during my project, how I solved them, and design an automatic system in deadline with the regard real-time constant simulation testing quick exposure to critical system bootloader. First challenge, loop overflow. Early in the development, system execution timeline began falling into the deadline because of string print function were looking CPU to ensure deterministic 10 milliseconds execution for our prime control loop. I complete step our text-based print and move to the structure binary telemetry frame offloaded to the background UART DMA channel. This drops CPU overhead down the near zero to grounded and real time schedule. And the second fall positive and jitter. During the split special safety testing raw and ultrasonic sensor reading module are producing sharp singular drop of the data and spirit due to the symmetric signal left unchecked. This would cause a false positive emergency braking alarm on the highway and resolve this by passing the raw input through the software moving average filter to the smooth output like 3 simple alarm state threshold. Ultimately, this challenge provided me biggest growth takeaway from his internship. I moved work basically software syntax into the true hardware software co-design and learning how the balance bandwidth constraint and manage the signal noise to build deterministic safe automatically and the safe environment. The brought me end of my presentation. Thank you all of you for time and attention through the over my EV ADAS project. I would love open up the floor and planning now. Please feel free ask to any question and share your feedback on my system architecture, that physical model of the telemetry pipelining.